Dear parents, welcome to the class 256, Machine Structure. So today we're going to start a new chapter, the memory technology. It's very important. I'm going to spend like next week as well in this chapter. A lot to learn here. All right, so be focused. Anybody remember about anything about the exception and interrupts? Time to review that. That's the right one. New, I think I should kill this. All right, so I think time for the attendance. 3. November 3rd. Angel Antunes, are you there? Angel Antunes. Oh. Arsania Talla.
Here.
Good. Shirley Ben. Shirley Daniel Ben.
Here.
Got you. Robert Boyce.
Here.
Philip Chen.
Here.
Jimmy Cheng.
Here.
Alyssa Chi.
Here.
John Cuevas.
Here.
Dankara BS. Jill Diora.
I'm here.
Trevor Eckler.
Here.
Jair Estrada.
Here.
Reis Ubani. Reis Ubani. Stephen Pong.
Here.
Christian Garcia Cortez.
Here.
Antonio Indindoli.
Here.
Anish Katka.
Yeah.
Ayush Kaul. Ayush Kaul. Sweetie Plamachin.
Here.
Matthew Lucirano.
Here.
Kenneth Leon.
Here.
Melody Long.
Here.
Ricardo Lopez.
Here.
Pragati Makani.
Here.
Philip Martinez.
Here.
Jen Maxwell. Sean Ng. Sean Ng. Sue Lam Ng. Scott Nguyen.
Here.
Sean Nguyen. Sean Nguyen. Young Dylan Pam.
Here.
Ayush Ramani. Luis Ramirez.
Here.
Luis here?
Luis.
Okay. Eric Rodriguez.
Here.
Eduardo Ruiz. Eduardo Ruiz. Andy Shai. Young So.
Here.
Dylan Suen. Stephen Johnny Trump,
Here.
Akash Thagarajan,
Here.
Nicholas Thomas,
Here.
Jonathan Valdez,
Here.
Jonathan Burgess, nope. Stephen Vesquez,
Here.
Rita Lesko,
I'm here.
Jie Cheng Wen,
Here.
Anthony Yu,
Here.
Jiwan Yu,
Here.
Justin Yu,
I'm here.
Good. Right, so I noticed that few students did not submit their assignment 3 and some missing other assignment 2. So reminder is that you still have a chance to do it. When you're late, I'll take some points, but still I'll credit. But before the final, I'll not do it. I'm telling you right now, you have a chance to do it now, this week. If you want to catch up, just do it. I'll look at it before the final and then I'll grade it. Important. So now we have 3 pieces of work. So I need 2 more assignments, actually 4. So 2 more assignments. One will come this week, I think, end of this week. And then we have 1 quiz and then a final. So like 4 pieces of work you need to do in order to complete this course. Of course, if you don't submit assignment, you may not be able to pass this course, but no problem. Next semester is coming. I'm teaching 2 sessions. You're welcome to join then if you want to repeat and make the university rich. I don't have an issue with that. I don't get much, I get portion of it. So university get richer when you repeat course and pay again. That's your call, okay? Now let's, okay, so anybody remember anything about interrupts and exceptions?
Hey, Professor, can you give me permission to record?
Yeah, sure. With that thing, participant. And
Isn't interrupt exception?
yeah,
This is Dylan Sibin.
Dylan, okay.
Isn't interrupt and exception basically just an error from like user input and stuff like that?
You try to. Why can't I do it? You go to the participant or? Yeah, I think it's participant.
You go to participants and then you find my name and you click on more and you click give permission to record or something like that.
Oh, yeah. Well, let's forget that. It says allow record local files. Yeah,
Thank you.
and there now. All right, so interrupts and exception. It's a small chapter, but it's important. Okay. So you need to remember that what is interrupts, the definition and examples, and also the exceptions and examples. The interrupt is events external to CPU, meaning something happened outside of the CPU, if some problems, issues that your program is not running or not giving you the right output. that you're expecting. So that's interrupts. And the exception and the examples are user input output and network events. And exceptions, the definition is the events happen internal to the CPU. Error conditions, memory leak, null pointer exception, memory access errors, error index out of bounds, stack overflow, divided by 0, arithmetic overflow. So divided by 0, it becomes infinite. So that kind of thing you can't solve. Both also called traps and signals. So interrupts and exception, also called traps and signals. Then the question comes, how you share it. How does the CPU service the trap? It jumps to a special system routine called trap handler. So you need to memorize this stuff because you may have a quiz in the quiz test, the class test. So they call a spatial routine or a trap handler or exception handler or interrupt service routine. And there are two of them. You remember, one is the cause register they create. Another one is the program counter. So what does the trap handler do? Depends on what type of error or exception or interrupt happens. How hardware is set. And then if it is minor, then just print a message. If it is major, then print error message and code out. As example for arithmetic overflow, here we ran it, we see it works, gives error message. And SPM's trap handler only does one thing, print error message. Remember that. It's another example here. And this chapter has not much, it's just that, and we have the, you don't have to worry about this, catch some more examples. And then this is for exception and interrupts. Goal. Extend MIPS hardware implementation discussed earlier to support interrupts and exceptions. How they do it? They add two new registers. Somebody's microphone is on. Can you turn it off, please? If you're not talking. Give me a thing. Your microphone is on. Okay. Add two new registers. Cause and exception program counter, EPC, call it. So this new register handle those exception and interrupts, okay? So how you can add those is in the diagram here. Multitasking operating system. Suppose two processes are running simultaneously on a system with one CPU. How does this work? So it's pretty simple. One is actually hold and another burst. CPU is time shared, so between processes. The timer interrupts is triggered by hardware periodically, and then two co-processors, 0 registers, count, incremented periodically by hardware. Compare when count equal to compare, timer interrupts occurs. Basically, they share the CPU. Okay, one is wait, another runs. The process 0 executes for some time, timer interrupts occurs, trap handler saves input for process 0, trap handler restores input for process 1. So just they use the process 1 and then another and another, and then save in the trap handler. And that's how they share. one CPU, two processes at the same time, multitasking. Okay, so that was in this chapter, not more than that. So just try to remember it. It is very important. In chapter 9, memory system. So memory is very vital part of a computer system. So you need to get information from your permanent memory to the temporary memory like RAM or SRAM or DRAM, and in order to process your data with CPU. So memory technology is very critical to have a good computer system. So learn about this, and cache memory is part of it. And then we learn about virtual memory and also operating system support a little bit, not much. We learn more about cache. Main memory. So the speed versus memory speed. CPU speed versus memory speed. Main memory, main storage for active programs based on dynamic random access memory like DRAM. And mesh pipeline organized into instruction memory and data memory. We saw that in this other slides. Each memory takes one cycle to access. Typical CPU clock rate 2 gigahertz. Cycle time 500 picoseconds. And then if you want to learn more about memory stuff, you can go to this link and learn more about this. What are DRAM speeds according to this Wikipedia? In 2009, the fastest DDR2 HDRAM double data rate. Synchronous DRAM, that's what they call it, DDR2, double data rate. Synchronous DRAM has cycle time less than 4 nanoseconds. Not good enough for pipeline design. Instruction memory and data memory are actually instruction cache and data cache. A cache, what is cache? Definition of cache here, okay? You need to memorize this. A cache is a smaller, faster memory between main memory and CPU. Between. See, the registers is in the memory. Inside the memory. Registers are inside the memory, but cache is not. It's between main memory and CPU. Using static RAM, SRAM technology. So that's the cache is, SRAM. Memory hierarchy concepts, very important. Memorize this. You have question in the quiz. Levels of memory hierarchy, registers, cache, main memory, disk and secondary storage. There's 4 types of memory. So the closer to the CPU, faster they are and expensive they are. Registers are faster than cache. Cache has a 3 level, 1, 2, 3. Main memory, dynamic RAM, and then you have the disk and secondary storage. The magnetic disk or flash drive and all those. So they are the slowest and they're the cheapest to get access to. SRAM, it takes 0.5 to 2.5 nanoseconds. And the price in 2008 survey, 2K to 5K per GB. DRAM, 50 to 70 nanoseconds access time. And it's 275 per year. I think now it's probably a lot cheaper than that. Disk 5 to meg to 20 meg nanoseconds access time. And it costs $0.2 to $2 per GB. Closer to CPU, small and fast, inexpensive. Further from CPU, large and slow, cheap. You can try to find the price, current price. Let's see, SRAM and DRAM, we can search it. So you can search the price. That's the price for SRAM. Okay. Are you, so I'm still sharing it. You can see my screen here.
Yes.
Okay. So this is the see this price there. Cypress Semiconductor, 2,491. Cypress HPE, DZ Key, server supply. So it's a different kind of company just advertising it. And if you look at here, SRAM is much more expensive than DRAM. A gigabyte of SRAM cache costs around 5,000, while a gigabyte of DRAM costs $20 to $75. Since SRAM is flip-flop, which can be made of 6 transistors, and SRAM needs more transistors to store 1 bit than DRAM does, which only uses a single transistor and capacitor. So see the price here. Who's cheaper? Of course, the DRAM is cheaper. But let's see the price in what's the eBay things. Let's look at eBay, how much it's selling. Yes, I have 4 gig, 2 gig, and 1. So this Protic one is $200, $250, and then $350, and so it's cheaper than before for sure, but still quite a bit of price. You see that. So that's the memory. Let's go to our lecture. Yeah, it's different now than before, but it's still expensive. Suppose we are running a program that works with some data. Most of the time, we are just executing a small number of instructions, working with a small amount of data. This is the principal locality observed in programs. So look at an example about just a story actually. So to understand the locality, so there are two kinds of locality: temporal locality and spatial locality. So what does it mean? There's an example in the book is story. Let's say if you want to write an article, let's say a paper for a semester paper or something, then you need to collect quite a few books. So if you have like 3 books and it doesn't cover all these things you need, then you need to go back to the shelves and come back with the books and then focus on your paper again. Then if you need something else, the reference material, then we go back to the shelves and come back. But if you have like most of the books you need, then you can just sit in your desk and focus on writing. You don't have to go out of the desk and go back to the shelves and find it and come back. So this is just an example of the locality. So the temporal locality is if an item is referenced, it will tend to be referenced again soon. If you recently brought a book to your desk to look at, you'll probably need to look at it again soon. So this is called a temporal locality. I think I have it here. Yeah, the 2 types of locality. If a memory address is referenced at the current time, the same address will be referenced again soon. So that's the temporal locality. You need to memorize this. Instructions in a loop, instructions in a recursive function, loop counters. This is the example of the temporal locality. Then spatial locality. If a memory address is referenced at the current time, an address close to it will be referenced soon. Sequential array access, iterating through array, state line code, basic block. That's the example of spatial lookup DT. If a memory address is referenced at a current time, an address close to it will be referenced soon. So that's other address. It's two, temporal and a spatial lookup. Technology issue, DRAM versus SRAM. So the main memory constructed from DRAM, dynamic random access memory. One transistor holds 1 bit. Destructive reads periodically refreshed. And the DRAM is organized as a dual inline memory modules, DIMMs, typically 8 to 16 DRAM chips per DIMM, usually 8 byte. That looks like those that we just looked at on here. Where's to memory? So the DIMM, dual inline memory modules. So DIMM stands for that. Dual inline memory module. Remember that. And then the DRAM is dynamic random access memory. One transistor holds 1 bit. Remember that, this is important. Destructive reads periodically refreshed. So it's time to time refreshed memory. And then typically 8 to 16 DRAM chips per DIMM, usually 8 bytes wide. A 1 gigabyte DDR2 DIMM look like this. It's 1 gig. Address divided into row and column. Send a row address and row access strobe. Read row of bits from memory array. Send column address and column access strobe. And select bits from within row. Send out to CPU. So it operates. Early DRAMs were asynchronous. Most fast DRAMs today are synchronous. So DRAM also synchronous now, but used to be synchronous. Then you can look at this PC magazine and learn about it more. DRAM block diagram is like this. Row address demultiplexer selects row. Performance consideration. DRAM much slower than CPU clock cycle time. Each memory access takes many cycles. Static RAM for caches. Static RAM basics reads are not destructive, no refresh is necessary. Typically 6 transistor per bit. There is 1 transistor 1 bit. Here 6 transistor per bit. DRAMs 4 to 8 times denser per chip than SRAM. SRAMs 8 to 16 times faster than DRAM. SRAMs 8 to 16 times as expensive as than DRAMs. So it's expensive, 16 times faster, and 8 times lighter than DRAMs. Read typically 6 transistors per bit. So this is the thing you need to remember. So we need to compare DRAM and SRAM. Terminology. Consider pair of connecting levels: cache, main memory, disk. Upper level is fast but small. Lower level is lower but larger. Goal: keep instructions or data in upper level when needed. Then we have all this definition. Heat: an access found in the upper level. Miss: an access not found in the upper level. Hit rate: number of hits divided by number of accesses. Miss rate: number of misses divided by number of accesses. Hit time: time for a hit. Miss time: time for a miss. Miss penalty: miss time minus hit time. CPU, cache, memory. That's the memory hierarchy. Remember that the register is in the CPU and cache is outside the CPU between memory on the CPU. Basic principles of cache. Usually, main memory much slower than CPU. Cache a small fast memory array close to CPU, basically in between main memory and CPU. AMD Opteron 64 KB L1 instruction cache, 64 KB L1 data cache, and 1 megabyte L2 cache. So this AMD has this kind of. Let's look at this Opteron and the here. AMD $64. Same Ryzen compact, $863. Now you can see that, like, when you buy a laptop, here, see this memory costs a lot. Opteron. To all our readers anyway, so they want money stuff. So the Opteron, and study this a little bit. AMD's x86 former server and workstation processor, and was the first processor which supported the AMD 64 instruction set architecture, generically as x86 64 or AMD 64. It was released in April 22, 2003 with the Sledgehammer core and was intended to compete in the server and workstation markets, particularly in the same segment as the Intel Xeon processor. Processor based on the AMD K10 microarchitecture were announced in September 10, 2007, featuring a new quad-core configuration. The most recently released Opteron CPUs are the Piledriver-based Opteron 4300 and 6300 series processors, codenamed Seoul, and Abu Dhabi, respectively. Why they named Seoul and Abu Dhabi? In January 2016, and first ARM V8A based Opteron branded SoC was released, though it is unclear what, if any, heritage with this Opteron branded product line shares the original Opteron technology other than intended use in the server space. There's a lot more information to give in here. You have features, you have the technical description, then you have models, different Opteron models. You have 130 nanometer SOI, Opteron 90, 65, different sizes. First generation bulldozer microarchitecture. Piledriver microarchitecture, Jaguar microarchitecture, they're different kind of name. Supercomputers. So you have lots of description and details here to learn. Just read through it if you're interested. I'm going to test you on this. Multi-core Opteron, multi-core processor. This is for the AMD. Yeah, AMD share gone higher today. So a few months ago it was like 85, now 100 plus. So, socket AM2, lots of information you can learn if you're keen in hardware. Okay, APUs. Feature table. Yeah, lots of information. You can look at it. A different name, city name, code name, process, data list, core. Santa Ana, Santa Rosa, is it Italy, Denmark? That's the code name. Interesting, Toronto. So you have all these details there, hardware. So different kind of cache. You have L2, L1, L3, L3 cache, L2 cache. So it's a different cluster level, L1 and L3, I think. See lots of details. I'm based on that. So you can see that in hardware it can be many model, many types. So that's the cache, AMD Opteron. Block or line, basic unit of information transferred between cache and the CPU. So the smallest piece is block or line. Simplest, one word block. Since cache is much smaller than the main memory, must hash 32-bit memory address to a small cache index. Then we learn about direct mapped cache with one word block. So when you draw this, look like this. Here's your main memory addresses, and here's your cache. The cache has the index and then its content. And this index connected to the contents of each location in a main memory. For just some examples, you're going to learn all of this: byte offset, index, and tag. So let me look at we have a diagram, basic cache. Direct map cache, a cache structure in which each memory location is mapped to exactly one location in the cache. So the diagram is here. Let's draw this. Direct mapped SCH. So how it look like is let's draw it. So we have a cache on the top, and there will be a small. Let's say we divide into 1, 2, 3, 4, 5, 6, 7, 8 pieces. So as this should be smaller. Divide into, can't even draw a straight line. Make 8 pieces. So that's the cache. And then each location has numbers. So 1, 1, 1, 1, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1. So from this way, 0, 1, 0, 0, 0, 1, right one like this. And then 0, 0, 0. And they have kind of color. So let's do some color. Third one, very colorful. let's say a special color. And then southern kind of brown color, the second one. And different There's two different. Let's stand out. Okay, fine. Now the memory is large, but we have how many pieces here? It's a lot. Let's see. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 19, 20, 21, 20, 22, 21, 22, 26, 27, 28, 29, 30, and 32. So 32. So the memory should be 32 pieces. So as one of my piece is like half. So maybe I think I should have drawn it in the middle. No. Okay, that's okay. We'll just draw the line. Maybe weird way of it. So we can draw a 32-bit. And just draw. Just assume it's 32 pieces. A sharper line. So that's 4. That's 8. From 16. And then double this with 32. It should be a straight line, but pretty bad at drawing. Never learned how to draw in the school. All right, so this should be a straight line. And the color should match. So let's take one, third one. So you used this color, I think. So the third one will be this color. This color. And then third, fourth, fifth, sixth, seventh. 4, 5, 6, 7 will be different color. Let's separate this color. Not much difference. Should go yellow. This should be yellow then. Basically, not black. So match with that. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 7, 8, 9, 10, 11. This should be this color. This color. This color. Just maybe this and that. And then this should be the same color. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19 should be not okay. So the 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. This will be the same color as this. and 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Whole thing should be solid color. Whatever. Let's assume they're the same color. And then the other color, the yellow one, I think, should be yellow. So the second one should be yellow here. And 3, 4, 5, 6, 7, 8, 9, 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. This one will be. And here, 8, 9, 10, 11, 12, 13, 15. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yes. All right, so this is the main memory, okay? Main memory. And this is the cache. So the relationship is like this. So you have a point here, and you connect with the cache. And then this should go to the yellow, should go to the yellow, like that. I think it should be side mapped. And then the green, go to the green. And this green also go to and the other green, the whole green should go to the green. Then yellow, all yellow should go to the yellow. They call it direct catch. All right, so the definition is, I mean, it's pretty bad drawing. Should be the cache should be in the middle, and then you'll look next to main mistake there. All right, so a cache structure in which they should write it down as definition. It's important. There's 3 kinds of cache. So it's direct, mapped cache. A cache structure a cache structure in which each memory location is mapped to exactly one location in the cache. Exactly one location in the cache. That's a direct mapped cache. You need to know this, and you need to be able to draw this diagram to connect. That is easy. You catch just before and just after reference the word action that is not initiated the cache. That'd be fine. So then go from literature here you need to read through block address, block, number of blocks in the cache. And then the next definition you need to remember is the tag. You need to understand what tag and index is. Tag, a field in a table. Tag. A field in a table. A field in a table used for a memory hierarchy. Used for a memory hierarchy. Okay, ARCHY that contains the address that contains pick a sharper pen. Contains the address information. The address information. Address information required to identify. Required to identify whether the associated block, whether the associated block in the hierarchy corresponds corresponds to a requested word. Requested word. So that's the tag. A field in a table used for a memory hierarchy that contains the address information required to identify whether the associated block in the hierarchy corresponds to a requested word. So that's called a tag. And there is a formula to calculate that. I'll give you an amount. Valid bit, a field bit, the tables of memory hierarchy that indicates that the state block in the hierarchy contains valid data. And this definition also required valid bit. So another definition is valid bit. Okay, valid bit. Valid bit. A field in the tables of a memory. A field in the tables of a memory. Tables of a memory hierarchy that indicates that indicates that the associated block associated block B. Associated block in the hierarchy contains valid data. That's a valid bit, just a bit. A field in the tables of a memory hierarchy that indicates that the associated block in the hierarchy contains valid data. That's a valid bit. So we learn about tag and valid bit. Now, few more. We learn about index too. What is index? Tag, which is used to compare with the value of the tag field of the cache. A cache index, which is used to select the group. All right. So the diagram here, but third statement cache size, bit in a cache. So some example about the cache and how do you calculate how many bits in the cache. Right through, and then write buffer, write back. Don't write too much over those. So as an example here, how many total bits are required for a direct map cache with 16 kilobyte should be of data and 4 word blocks, assuming a 32-bit address. Now, there are some methods to calculate that. So you learn that. Not in that way, but cache means let's go back to the cache performance calculation and we'll do some as well. Then have the other two types of cache. Let's learn those 2 types of cache and then we'll look at the calculation in the next class. Okay, so one is the direct map cache. Another one is, so it's number 2 will be, so that's number 1 and this is this is 1. That's the other definition, tag and valid bit. It's not going down. Some issues. Okay, so another definition is the set. So it's 2 of them. One is fully associated cache, another one is set associated cache. Let's say put set associated cache first. Set associative cache. So the kind. So the definition will be a cache that has a fixed number of locations fixed number of locations where each block can be placed. Each block can be placed. So that's the set associative cache. So the diagram here, you might probably know that. Another diagram, I think the PDF slide you may have it, we'll look at that then. So that's the one set associative definition, a cache that has a fixed number of locations where each block can be placed. And number 3, fully associative cache. fully associative cache. So the fully associative cache, a cache structure, right, CD, a cache structure in which a block can be placed in any location. Any location in the cache. So that's the third one, fully associative. So three types of cache: direct mapped, set associative, fully associative. Fully associative is a cache structure in which a block can be placed in any location. And set associative is a cache that has a fixed number of locations where each block can be placed. And the direct map is directly connected with one block in the memory. So a cache structure in which memory location is mapped to exactly one location in the cache. So that's the direct. So I need to memorize these three, and to understand how this cache thing works. And let's go back to the PowerPoint and PDF slides. So here is an example. 32-bit memory address into log n bit cache index. Divide 32-bit address into byte offset, cache index, and tag. So there's three things you need to calculate. So tag, we learned about tag already. And cache indexes will be log of n. N is the number of blocks. So you have to find number of blocks. It's given, sometimes given number of blocks. And then you figure out log of n, that should be your index. And then tag will be index minus offset. So we'll see that how we calculate. Each block in a cache may contain a block from several different memory addresses. The tag identifies which memory blocks is in that cache. So let's look at an example. Will it be tag data? Okay. Here's an example. Suppose direct map cache has 64 kilobyte of data and one word blocks. How many total bits does it contain? 32-bit memory address. So it's asking how many total bits. There's example, bit. This is the. So it's another example here. So 4 kilobyte direct map cache, one word blocks loop is at address, that particular address. So how do you figure out the offset, index, and tag? Here, we see that on the right side, the offset is 2 bits. How? So 4 KB, so 4 you can write 2 to the power 2. So this power is the offset, 2 to the power 2. And then number of blocks will be, you divide the 4 KB divided by one word block. So one word block means 4 bytes. So you divide by 4, 1 KB, that's your index. So 1 KB, log of 1 KB should be your index. So log of the number of blocks. So log of 1 KB will be your blocks, and tag will be your total 32 minus your index minus offset. So that will be the tag. So that's the formula to calculate tags. So let's write that. think it should be somewhere written here. So the MAPE set shows the example in MAPE, but we're not interested in MAPE launch. Usually one instruction cache, one data cache, pipeline, multi-word blocks. Here's the formula. Number of blocks in a cache will be the size, the cache size, and the block size divided by cache size divided by block. So you have number of blocks in a cache. And number of bits in a block offset, like offset will be log of B. So log of B is the number of blocks. That's the offset. And then index is log of cache size divided by block. So it's actually number of blocks. So index is log of number of blocks. And offset is log of B. B is the size, block size. So log of block size will be the offset. And number of blocks in the cache will be that size divided by the cache size. So you see that here, this example here. The 4 KB is direct map cache size. So cache size divided by word size, that will number of blocks. And log of number of blocks will be the index. And log of the word block size, that's the offset. So if we write it down, offset is here. So put you back in our so you further down. So 3 things you need to calculate here: offset, index, tag. Offset is log of B, actually the cache size, no, block size of block. Index is log of number of blocks. Number of block is the cache size divided by block size. And the tag is minus the offset index minus offset. So this is the formula. So if you look at that example, we go back. Here, our cache size is 4 KB. So 4 KB number of 4, and the offset will be, and the one word block is the block size. So one word is actually the 32-bit 4 byte. So you need to convert it to, so bit, one word block means actually 32-bit. So it's 4 bytes. Then you offset will be log of 4 bytes. That's why it says 2 bits. How the log works is we have, let's say 32 bits per byte. So if you say the offset will be Come on, go down. So the offset will be for that example, log of 4 bytes. So log 4, you can write log of 2 to the power 2. So then you have to have 2 log 2, that's actually 2. Because this is a base 2 log, so we have log 2, it's actually 1. So 2 times 1, actually 2. So this 2 times 1 is 2. So that's how you get to this log. Offset is log of 4, actually 2. So 2 will be the offset. And then the index is log of block size divided by cache size. So index will be, log of, we call it C by B, block size and cache size. So cache size was 4 KB divided by 1 KB. That's basically 4 KB. So 4 KB and then you make here. Yeah, 1 KB. So now log of 1 KB you have to do. Sorry, 4 bytes and 4 KB. So it should be 1 KB. Yeah, that's right. Should be 1 KB. Oops. 4 bytes. Yeah, so that should be 1 KB. That's right. So 4 KB divided by 1 KB or 1 bytes. Actually, 4 bytes here and here 4,000 bytes. So that's why 1K. You were here. So here, 1 KB basically is 4 bytes, not KB. So this is KB, 4 KB, this is 4 bytes. So if you divide by that, then you will get 1 KB. 1 KB is 1,000. So you can write, go back here. So log of 1 KB is 1024, isn't it? Then bits, then you can write log of 10 to the power 10. You can write 10 base log 10, and then you have 10 times 1, log 10 will be 10, 1, and then you have 10. So that's how they got the index is 10. Yeah, index is 10. And then tag will be 32 minus 10 minus 2 is 20 for this. So the tag will be (32) minus index minus offset. That is 32 minus 10 minus 2. So that's 20. That's the tag. So we will learn about that more. We'll look at more examples on how you can do this, finding out tag, index, and offset. But that's the formula. This is the formula that's here. All right, I think we're at the tail end of the time, so see you in the next class. So try to learn all this definition and read the literature from the slides and from the book, whatever resources you have. All right, so take care and see you in the next class.
Thank you.
You're welcome.